Good morning. In this video, we will discuss about anharmonic oscillator. In the last video, we considered a vibrating diatomic molecule as a simple harmonic oscillator, and we treated the diatomic molecule as two masses connected by a spring. But connected by a spring. But in case of a real diatomic molecules, the bonds are not perfectly elastic and they do not obey exactly the laws of a simple harmonic motion. In case of a real diatomic molecules, the bonds are not perfectly elastic because if the bonds were perfectly elastic, then the bonds will not break even for very large displacement. We all know that if you consider the HCl molecule, if you consider HCl molecule, and if you push this hydrogen atom to a if the displacement is very large, that is നമ്മൾ hydrogen atomത്തിനെ നല്ലോണം പിടിച്ച് വലിച്ചു കഴിഞ്ഞാൽ after a certain limit this bond will break. That is, if the bonds were perfectly elastic, then it will not undergo a dissociation. So you can say that in the case of a real diatomic molecules, the bonds are not perfectly elastic, and simple harmonic oscillator approximation calls good for only small amplitude vibration and fails for very large amplitude vibration. And you can see that the green curve represents a potential curve of a simple harmonic oscillator. So we can see that the potential is a parabolic. The potential associated with the simple harmonic oscillator is a parabolic curve, so it will not undergo dissociation even for very large amplitude vibration. But in real case of real diatomic molecules, it will undergo dissociation, and in the case of a real situation, the potential curve has to be like this, as given by this blue curve, where you can see that for for a very large displacement, the molecule will undergo dissociation. And this kind of oscillating diatomic molecules, we can treat this kind of oscillating diatomic molecule as a anharmonic oscillator. Anharmonic oscillator. In case of anharmonic oscillator, this is it. This is considered to be it. In case of an anharmonic oscillator, they are characterized by the nonlinear dependence of the restraining force on the displacement. And the potential which is used to describe the anharmonic oscillator is known as the Morse potential or Morse function. And this given by the equation E is equal to D equilibrium into 1 minus E raised to A R equilibrium minus R the whole square, where D equilibrium is the dissociation energy, R equilibrium is the internuclear distance corresponding to minimum energy, A equal to constant which controls the width of the potential curve, and this empirical relation was put forwarded by P.M. Morse, and therefore it is also known as Morse function. And by solving the Schrodinger wave equation for anharmonic oscillator, the allowed vibration energy level is found to be EV is equal to V plus 1 by 2 omega bar E minus V plus 1 by 2 the whole square omega bar E chi E centimeter raised to minus 1, where omega bar E is the equilibrium oscillation frequency and chi E is the anharmonicity constant. And it is a small paucity, and it is always small and paucity. And due to the presence of this anharmonicity constant, the vibrational levels crowd more closely together with each other by increasing. So we can see in case of a simple harmonic oscillator, we have seen that all the vibration energy levels are equally spaced. But in case of an anharmonic oscillator, the vibrational levels are more closely packed. That is, you can see that the gap between the vibrational energy level decreases as V increases, or the vibrational energy levels are more closely packed, are crowded more closely together on increasing V. That is, this, if you see this gap between V is equal to 4 and 5, and look at the energy gap between 3 and 4. So you can see as the as V increases, the vibration energy levels start more closely together. And the selection rule for an unharmonic oscillator is given by delta V is equal to plus or minus 1, plus or minus 2, plus or minus 3. That is, all the transition from V is equal to 0 to any number, 0 to 1, 0 to 3, 0 to 4. All the transitions are allowed according to the selection rule, and the transition from 1 to 2, 1 to 3, 1 to 4, and or 2 to 3, 2 to 4, 2 to 5, 2 to 6. All the transitions are allowed according to an unharmonic oscillator model. And but since in case but in and but the population or the in case of most of the molecules are in the vibrational ground state at room temperature. That is, in case at room temperature, most of the molecules occupy V is equal to 0 state. So the transition will occur from V is equal to 0 state. That is, transition from V is equal to 0 to 0. Transition from V is equal to 0 state is most probable, because most of the molecules at room temperature occupy this V is equal to 0 state. And the transition from V is equal to 0 to 1, transition corresponding to V is equal to 0 to 1 transition is known as fundamental transition. And the transition corresponding to from V is equal to 0 to 2 is known as the 0 to 2, and V is equal to 0 to 3, or transition corresponding to delta V is equal to plus or minus 2, plus or minus 3 are known as overtone. That is, 0 to 2 transitions is known as first overtone, and 0 to 3 transition is known as the second overtone. And so transition from V is equal to 0 to V is equal to 1 is known as the fundamental transition, and the energy is given by omega bar into 1 minus 2 chi e centimeter raised to minus 1. And the additional bands that occur in the IR spectrum at frequency higher than the fundamental transition corresponding to delta V is equal to plus or minus 2, plus or minus 3 are known as overtone. The transition from V is equal to 0 to 2 is known as first overtone, and the energy is given by 2 omega bar 1 minus 3 chi e centimeter raised to minus 1. And the transition from 0 to 3 is known as the second overtone, and the energy is given by 3 omega bar 1 minus 4 chi e centimeter raised to minus 1. And the intensity of the signal follows the order. Fundamental transition is more probable than first overtone followed by second overtone. I have already mentioned that at room temperature, most of the molecules are present in the V is equal to 0 state. But as most of the molecule occupies V is equal to 0 state. But as the temperature is raised, the population in the V is equal to 1 state becomes more appreciable. Because on raising or at temperature കൂടുന്നതനുസരിച്ച് molecules in energy കൂടും. അതുകൊണ്ട് the molecule will go and occupy the V is equal to 1 state. So becomes appreciable. So transition from V is equal to 1 to V equal to 2 will be observed at high temperature. നമ്മൾ എത്ര നേരം പറഞ്ഞത് room temperature molecules V is equal to 0 state ആയിരിക്കും. So all the transitions of V is equal to 0 state ആയിരിക്കും starting 0 to 1, 0 to 2, 0 to 3. പക്ഷെ high temperature അല്ലെങ്കിൽ temperature കൂടുമ്പോൾ എന്താ സംഭവിക്കുന്നത് വെച്ചാൽ moleculesന് കൂടുതൽ energy കിട്ടും. So it can occupy the V is equal to 1 state. So as a result, the transition from V is equal to 1 to V is equal to 2 will also be observed at slightly lower wavelength than the fundamental vibrational frequency. Slightly lower wavelengths than the fundamentals, and these transitions are called the hot bands. കാരണം temperature കൂടുമ്പോഴാണ് molecules V is equal to 0 state in V is equal to 1 state. അല്ലെങ്കിൽ high temperature transition arising from V is equal to 1 or V is equal to 1 to 2 transition നിങ്ങൾ ഒബ്സർവ് ചെയ്യാൻ പറ്റുന്നുണ്ട്. ആ ഒരു ട്രാൻസിഷനാണ് നമ്മൾ ഹോട്ട് ബാൻഡ് എന്ന് പറയുന്നത്. ഹോട്ട് ബാൻഡ് എന്ന് പറയുന്നത് കാരണം ഹൈ ടെമ്പറേച്ചർ ഉണ്ടെങ്കിൽ മാത്രമേ മോളിക്യൂൾസ് V is equal to 1 സ്റ്റേറ്റിലേക്ക് പോകുള്ളൂ. അപ്പോൾ V is equal to 1 സ്റ്റേറ്റിൽ നിന്ന് അത് ട്രാൻസിഷൻ V is equal to 1 സ്റ്റേറ്റിൽ നിന്ന് V is equal to 2 ലേക്ക് പോകുകയാണെങ്കിൽ ആ ഒരു ട്രാൻസിഷനാണ് നമ്മൾ hot band എന്ന് പറയുന്നത്. The hot bands are because high temperature is required for the hot band. The population of the excited vibrational state V is equal to 1 become appreciable at high temperature. And this is known as hot bands. This is also known as hot band because it is observed at high temperature, and this high temperature is required for their occurrence. So the transition from V is equal to 1 state will be observed at high temperature. And these bands are known as hot bands, and the energy corresponding to V equal to 1 to V is equal to state is given by omega pi 1 minus 4 chi centimeter raised to minus 1. So this is all about the unharmonic oscillator. Hope you have understood it, and we will have to do some problems or work out some problems on this unharmonic oscillator model by using on vibration spectroscopy in the next class. Thank you.